What's up guys, it's me Sir Ernest, and today we're going to solve 2-34 of Thornton and Marion 5th edition. The problem reads, a particle is released from rest at y equal to 0 and falls under the influence of gravity and air resistance. Find the relationship between the v and the distance of falling y when the air resistance is equal to alpha v and beta v squared. Okay, so in this video we're going to solve first letter A, and in the next video we're going to solve letter B. Okay, so for letter A, the resistive force will be equal to negative alpha v. Okay, so under the influence of gravity, so this particle will now experience two forces. Force exerted, gravity downward, and opposing that would be your resistive force. So let's say we choose downward to be positive, so that the velocity that is downward will also be positive. Okay, so this together with the gravitational force, the equation of motion becomes Fg plus Fr equals m dv dt, or this will now be equal to mg minus alpha v. So mg here is positive because we set again that the direction is negative downward. Okay, things will be a little bit different if you choose upward to be positive. Okay, so anyway, so this mg minus alpha v, this is equal to m times the derivative of v with respect to time. So from here we can solve this differential equation. So this becomes m dv over mg minus alpha v, and this is equal to dt. Then we can integrate them. So again, it started from rest at time equal to 0, and at time later t, the velocity is v. Of course, we can solve this differential, this integral. This becomes ln, natural logarithm of 1 over L, etc. So the end result here is v will now be equal to mg over alpha times 1 minus e to the negative alpha t over m. Okay, so from here to here you can just solve this at your own time. Okay, so hint, this becomes a natural logarithm. That's why there is an exponential here. Okay, so we know that this is derivative of y with respect to x. So integrating this further becomes integral of dy from 0 to y. This is equal to integral from 0 to t of mg over alpha plus 1 minus e to the negative alpha t over m dt. Okay, so again you can do the integration later, but the point is that the y will now be equal to mg over alpha times negative m over alpha plus t plus m over alpha e to the negative alpha t over m. Now the question is, you would like to find the relationship between the velocity and the position functions. So recall, you can see that from the position or from the velocity function, we can actually calculate t from here. So we can actually compute it here that t, this is t, this will now be negative m over alpha times ln of 1 minus alpha v over mg. Okay, so we can use this here. So substitute this expression or this equation for t here. Okay, and then you can just do a series of manipulation, and then you'll end up with y will now become a function of x, or a function of v, which is equal to negative m squared g over alpha squared times ln of 1 minus alpha v over mg minus mv over alpha. Now this is now the relationship between v and y if the resistance force or the air resistance is a linear function of your velocity. Okay, so letter B will just be left as an exercise, where Fr will now be equal to negative beta v squared. Okay, you can just refer to the notes to the detailed function, but a series we can actually write most important equations here. For example, the resulting velocity function would be equal to a times the hyperbolic tangent of a beta t over m, where a is square root of mg over beta. So that will be your velocity function, and then the resulting relationship between y and v will just be equal to negative m over 2 beta times ln of 1 minus beta v squared over mg. So this is now the result of letter B. Okay, you can just refer to the notes for the most detailed solution available to you, but this will be your resulting function. Okay, so you notice that for air resistance, that is a bit complicated, like b beta v squared. The velocity or the position function, so function of velocity, will have a much different function. Okay, that's it. That's your solution to problem 2.34. Thank you guys for watching, and I'll see you guys in the next video. Bye.